Yes, thank you very much. Do you hear me, first of all? Yes.
Yeah.
Thank you very much, Alexey, for introduction. And in fact, I will make not very strongly scientific talk. I want also to share some personal feeling about all this nice community, and that's why I want to present some sort of historical overview how I joined your team and what we made during this period of time. So this work in particular is just some part of the work, the most recent one, but the history is much longer. And what I want to start with, the picture that I usually show, this is the microcavity that we all know, the schematical design. And the most important difference from the two-dimensional system compared to the bulk materials that was widely studied before, the advent of the microcavity field, is the fact that in bulk material, when you increase your pump and study OPO or some other regimes, usually you can gradually increase the intensity of the pumping field. Opposite to this situation, in case of the microcavity, as you know, we have what is called bistability, and this is a very important difference between bulk and 2D regimes, because when we change the intensity of the input field, the output field, or the field inside the cavity that essentially controls all the processes inside the cavity, it jumps abruptly at some conditions, and this changes strongly the processes. And we found it and draw attention of our community to this important fact, and it results in some very different behavior of the scattering compared to the conventional three-dimensional one. After that, we turn to the picture that Guillaume has already shown. This is multi-stability, and finally, what I will talk about is the pseudo-spin precession that also relates to this issue. But let's go further. And here I want just to show this picture that probably a lot of you are aware of. At the time I made this picture, I was not yet acquainted, for instance, with Guillaume, Fabrice, and a lot of other guys. But thanks to this Philips series, I got a lot of friends, and I'm really very happy with all this series. So now, coming back to some physics, this is the schematic equations that we use to describe all this stuff. As Alexey mentioned, we can derive equations for electric field and polarization, excitonic polarization inside the microcavity. And the most important feature is that excitonic resonance, it is nonlinear one, and its resonant frequency strongly depend on the magnitude of the excitonic polarization. So this is certainly nonlinear equation, and from this nonlinearity, all the bistability and multistability process arises. So I will shortly show you that when we increase and study the time dynamics of our pumping system, for instance, we with time gradually increase our external field intensity, and you see this is dashed line that grows smoothly, but at some level of the pumping, we see abrupt rise of both polariton density and internal absorption, and it results in the fact that the scattering here appears to be much stronger. We have two essentially regimes of parametric scattering. The first one, where we have small pump inside, it is more or less standard picture. In the spectral range, you can see that it is the smooth and standard OPO regime where we have pump and signal and IDA. And above the threshold, we see a strong randomization of the scattering picture, and it's more or less turbulent. Okay, now I want to switch to another turbulence that I hope those who was in Clermont-Ferrand, you know that this is the place certainly where it is very natural to study light-matter interaction, and this is what I just showed, because we enjoy enormous, beautiful sunrises where we're living in Clermont-Ferrand. Then the next cathedral, I think everybody knows that this is Cathedral of Clermont-Ferrand, but what was a bit surprise for me, it is when I found this stained glass there, and at the time I saw it, first of all, it resembles obviously polaritonic branch, but not exactly. But if you know the polaritons in quantum two systems, in photonic systems, they look exactly like that. It is not very old stained glass, but still it was more or less, I think, created slightly before, as far as I know, Alexey joined Clermont-Ferrand. Is it coincidence or not? I don't know, but anyway, I like this stained glass very much. So coming back to polarization stuff. So the previous pictures I have shown you, they were for scalar problem, for neglecting the polarization. In fact, we know that excitonic field is a vector field and has two polarizations, sigma plus or sigma minus, or xy as you like. And the simple situation is when these nonlinear constants are the same. Then and only then we can say that the model is essentially scalar. Whatever polarization of external pump is, we have more or less the same internal fields, and polarization, if I show it by this color, of the internal field, this is psi plus, psi minus, they follow the polarization of external field. And in this sense, the problem remains more or less trivial. However, and what is very important, it corresponds to reality. In fact, these two constants, as you know, they are different, and cross polarization interaction constant is strongly smaller than the polarization constant of direct interaction, and moreover, you can even assume it to be zero. And in this particular case, you obviously see from these two equations that describe how the polarizations of internal field depends on the external field. You see that the ratio of these two polarizations, they are not the same in case these two polarizations are different. And this shows that polarization of internal field and external field, they are different, and this is the problem that should be addressed. And it is simple to consider the situation just for purely sigma plus or purely sigma minus polarizations. Then we resemble this as shape curve, the famous shape curve of the standard nonlinear oscillator. But if we go away from this simple situation, then the picture appears a bit more tricky, and you can understand where it came from. Because we have two oscillators that can be excited more or less independently, and then depending on the trajectory or on the plane of the external pump, we can find very peculiar trajectories of the internal field in the cavity. And if I draw this picture and show what is the internal field inside the structure, you see how fancy it is. So the low intensity range, where the system is more or less linear, it's more or less resembles the trivial situation when the polarization inside corresponds to polarization outside. It is where we can neglect the nonlinear shift. But as soon as we need to account for the nonlinear shift, we see the very peculiar multi-stable regime of internal field in respect to the external field. Another way of representing this data is to plot not psi as a function of input external field, and in fact you see it is not at all a function. It is multi-valued function. But the inverse transformation, if you ask what is the external pump as a function of internal field, this is certainly the function, as can be seen from this equation. And this surface looks like this one, and it is maybe more easy to analyze with this picture how you can and where you can jump. Here, what is important to understand is from this picture, we see that not all the values of the internal fields, they are accessible from outside. And this is an important difference between the two-dimensional situation and three-dimensional situation. Because here we really have a large area of the values of the internal fields that are not accessible. And that's why if you use some model where you keep the internal field as a control parameter and you find some threshold, you need to check that this threshold is really accessible from the outside. Otherwise, your excitation will, your regimes of the transmission will be much more stronger, much more abrupt compared to what you can expect from the symmetry. Okay, this work we have presented at another polarization conference that I show here, and who knows what is it? I guess you all understand that this is Cuba. And here, as I realized now, we have first observed the quantum entanglement state of our chairman. You see Alexei, he's simultaneously speaking to the audience and chairing the session. So this, I think, the first experimental observation of quantum entanglement of the chairman. So now let me go further. And at the same time, more or less, there was this nice paper published by also a team from Clermont. And I was not participating there, but it also deals with the polarization splitting. And it shows that this topic is certainly very well developed everywhere. But now I will make a large jump and will go to the paper that I want to discuss now. It is the experimental paper that we made with Vladimir Kulakovsky, and samples were prepared by the professor Sven Hofling group. And the question was the following: what will happen if we have the linearly split system with two states shown here, and we excite we select the polarization of our pump in such a way that we excite along the upper linear split state. The situation when we excite along lower linear states, it's well known, because when we have nonlinear condensate, we know that condensate want to be linearly polarized in this ground state, and this polarization will be pinned by the splitting. And if we excite along the lower linear split state, then it will be just linearly polarized. But what happened if we excite along the upper split polarized state? And experimental results were very clear. It was a time-resolved polarization measurement. And you see that, first of all, if we have the excitation of the order of several or tenths of picoseconds or so, depending on the intensity, if you look just on the intensity, then you see nothing special. For small excitation power, you see this dependence. For high excitation power, this dependence, they look more or less similar. But on the other side, if you look on the dependence of these polarizations, on the polarization state of your luminescence, then you will see that for a small intensity, your polarization is excited along the upper state, and then it more or less relaxes to zero. So you lose your polarization. But on the other side, what is interesting, then if you excite with strong polarization, strong intensity, then you see, first of all, these strong oscillations of your polarization, and you observe the polarization inversion. So your light becomes more linearly polarized along the ground state, that more or less natural. But what is interesting, that in case of small intensity, it doesn't happen. So because here we have already not driven the regime of our cavity oscillator, but rather free decay, the question was, what are the possible states of the condensate there? And moreover, experiment was showing that the coherency of all the area that was analyzed, it was very, very good. So the coherence length was measured to be up to 20 or even 40 micrometers, depending on the time. And you see that at the beginning, it's practically coherent. And then after 130 picoseconds, of course, coherence degrade, but not so strongly. If you compare, for example, the intensity, photoluminescence intensity drops more than order of magnitude, but the coherence function drops, but not so significant. So we can consider the system to be more or less coherent, and that's why the simple possible approximation is just to study the one coherent spinor that have no special dispersion, special dependence, and that's it. So now, okay, let's look on this simple Hamiltonian and ask ourselves, what can be the stationary solutions of this equation? You can try to do it directly by finding out the eigenfunction of, not eigenfunction, but this is nonlinear Hamiltonian, so it's some analog of eigenfunction, so you should find the eigensolution of this nonlinear equation. But it appears that it is much more convenient to work in the pseudo-spin language, and I don't think I need to remind you this concept. Important point is, if you decompose your density matrix through the Pauli matrices, and then you can easily find out that this famous equation is reduced to another one, famous equation of the precession of the pseudo-spin along the effective omega field. And what is important, that all you, I think, know, that this field that is precessing, it is composed from the linear terms plus this nonlinear term that I do not remember. Alexei probably can help me, I think it is called self-induced Larmor precession, but
yes,
in what
yes,
your
exactly,
papers
yes.
that was first made, to be honest, I'm not sure that I know the first reference. But anyway, I think it is what was also made in Clermont for polaritons, I believe, yeah? If I'm not mistaken, or if I'm wrong, just correct me.
You are absolutely correct, Kolya.
Yes. But anyway,
but I have to remind you that you have two minutes.
Oh, then I will go very quickly. Sorry, I want to show some nice pictures and then. So what I like here is that the equation in this language is very simple. It relates to pseudo-spin components, and you can draw these exact curves and characterize the energies and polarization states. And I really want to go quickly. The point is that maybe together with these equations, you can run quick dynamics, and these dynamics show you precession for low density along these poles and linear polarizations. But for high intensity, you see that precession starts to be either around sigma plus or sigma minus. And by the way, Alex, it resembles me very strongly the picture that you have shown in your talk. So maybe we can think, because in my opinion, this is a sort of multi-stability, but okay, maybe we can use another language. This is the dynamical system that if you start to account for the decay of our polariton, then we see that dynamics amplitudes going down, and we have some particular precessions. And in the end, we can see that the average energy indeed goes down and polarization is changing as it is in the experiment. Okay, so that's it. And more or less, once again, I want to thank strongly all the Clermont community for the hospitality when I was there. And I just show these conclusions and this rainbow that we like very much. And I want also to show these photos. I think, Alexei, you know Amir Vasson and remember him very well.
Of course.
Yes, and the next speaker, Joel, is also here, so I'm very pleased to find this photo, and I hope he recalled these nice meetings at Amir Vasson home. And then I just want as a reminder to show these brave guys who are chairing our session and not only sitting with us at the table, but rising and climbing to the very dangerous mountains close to Clermont-Ferrand. And this is just our present meeting that I hope one day will appear not only on the Zoom screen, but also in Clermont-Ferrand. So now I just want to thank everybody for their attention, and sorry
Thank you very much.
Late.
Thank you, Kolya. Thank you. We now have time for a couple of short questions.
Yes. Yes. We can save time for next speakers. Yeah.
But I mean, as a chairman, I feel obliged still to ask you a question.
No, Alex. Well, once again, I just want to show some photos. And
no, Olivier. Sorry,
yes.
No, I don't need to do it because Olivier has raised hand. So Olivier, please.
Olivier saved you. Okay, great.
Hi, thank you very much for this talk.
Mm-hmm.
And, I was wondering, in this experiment that you showed with polarization, multi-stability, how many quantum well is there in the sample used?
Well, this is a very good question. I'm afraid I cannot tell you just now. Well, if Sven is here, maybe he can tell us what was his sample. But I think it was sample with 12, I believe, quantum wells positioned active nodes. But I'm sorry, I'm
okay, but
what I know the parameters. The parameters of the splitting. Well, it was essentially the rapid splitting was quite large, I think. But what was important for us, it was this linear splitting where it is. Yes, it's here. You see, so the linear splitting was something like 80 microelectron volts. So it was not really very strong, but it was splitting at k equals 0. So it was it was deformation induced, I believe, splitting. And this circular splitting you should just more or less made for making calculations robust. It's not important at all.
Thank you.
Okay, thanks a lot. We are perfectly in time, so thank you, Nikolay, again for beautiful pictures and a very nice talk.